Hi, my name is Keith Barker, and I'm glad to have the opportunity to walk you through the nuts and bolts and pieces of Frame Relay. So let's begin. Our journey into the world of Frame Relay begins with making sure that we're clear how Ethernet works. Ethernet is broadcast based and it's multi-access. Multi-access meaning there's more than two devices or can be more than two devices in a specific VLAN. So in any specific VLAN we might have 5, 10, 100, 500 possible hosts, and we all have the ability, any host on that network, to send a broadcast frame and every other device can see it. It's very handy when we resolve layer 3 to layer 2 addresses, for example with using ARP. So Ethernet is a multi-access broadcast media. So in this multi-access broadcast-based network, doing resolution of layer 3 addresses to the appropriate layer 2 address, MAC address, is easy with ARP. We simply send out a broadcast that goes to every possible host on that VLAN, and the person with the associated IP address we're looking for responds with that person's MAC address. So ARP works because it's a broadcast-based network. So what exactly is non-broadcast multi-access? Oh, it's so simple. The multi-access part simply means we have more than two devices. So maybe we have 3 devices sitting on the 10 subnet. Super, no problem there. The non-broadcast nature is because we don't really have full mesh connectivity every time we work with Frame Relay. Maybe you'll have a headquarters site with a permanent virtual circuit going to spoke 1 and another permanent virtual circuit going to spoke 2. But you know what? Spoke 1 and Spoke 2 don't have direct connectivity to each other. So there's no broadcast support, if you will, where one device, any device, can send out a frame and everybody will hear it. And that's why we have some issue with layer 3 to layer 2 resolution, or at least a reason to learn about it so we can correctly make a non-broadcast multi-access network like Frame Relay work correctly. So on Frame Relay, we have some special mechanisms that we can use to resolve the layer 2 address of the next hop. Now with Frame Relay, it's the DELC, the Data Link Connection Identifier, that identifies the pipe that goes down to the peer. Imagine Frame Relay as a bunch of PVC pipes. 1 inch, quarter inch, 3/4 inch, doesn't really matter, but as long as you can visualize that pipe that goes from one site down to the other, the question is, how does a local router know which pipe to send it down? Maybe I'm the headquarter and I've got 5 different pipes. Well, the pipes are all labeled at the headquarter end. Maybe they're labeled 1, 2, 3, 4, and 5. And that's the ingress that the headquarters router can use to forward traffic. It knows, oh, I have a mapping of the host at 10.0.0.2 goes down DELC 501, for example. And it would just keep track of that either through dynamically learned mappings or static mappings. Remember, Frame Relay DELCs are on-ramps. Now once I send traffic down DELC 501, at the other end, at the far side, maybe they have a locally assigned DELC of 234. It doesn't even matter. As long as we get it into the pipe at the right DELC number, it's the Frame Relay service provider's job to forward it to its final destination. So here's how inverse ARP works. It's dynamic. If I have an IP address on a Frame Relay interface, I'm going to do an inverse ARP request. It basically says this: I'd like to know who's at the other end of this pipe. Now if you have a device at the other end of that pipe who also supports inverse ARP, it will respond, and it will respond with its IP address. When that response comes back, it'll say, oh, there's a device at the end of this PVC, this end of this permanent virtual circuit, and its IP address is 1234. And that's how inverse ARP operates, dynamically allowing 2 devices on Frame Relay to learn the person, the entity at the other end of the pipe. So if there's no permanent virtual circuit between 2 devices, it doesn't matter how many times you enable inverse ARP, it's on by default, they will not be able to resolve each other because there's no PVC. So just to resolve the two ends IP addresses for the benefit of the party at the other end of the pipe. That's how inverse ARP works with frame relay. Let's talk about the corporate headquarters site. Perhaps you have the headquarters site with several remote sites out there that you need to reach. Well, the headquarters site, if we use a multi-point interface, and that could be frame relay configured on the physical interface, for example, maybe serial 0/0/0, or we could have a multi-point sub interface. The key is with a multi-point interface is that we are able to terminate multiple permanent virtual circuits on that same interface. So most likely in a headquarters scenario, the trick is, well, if headquarters has 5 PVCs coming into it, headquarters has to know somehow the correct PVC to send traffic to site 1 and the correct PVC to send traffic to site 2 and the IP addresses at the other end of those pipes, and that's where the frame relay mappings come into place. We certainly could use inverse ARP, that would work, or we could do static mappings. Both are valid scenarios and are needed if, well, one of those methods is needed, mappings are needed, if we're using a multi-point type interface with frame relay. Another option that we can use, especially if it's at the spoke where they only have one PVC anyway, we could use a point-to-point sub-interface. Now, point-to-point versus multi-point. What's the big deal, Keith? Well, a point-to-point is going to terminate one PVC, one DELC identifier for a circuit. That's it. Where a multi-point sub-interface or a multi-point physical interface could terminate multiple PVCs coming in. That's the only difference. Well, if we have a point-to-point sub-interface, we really don't need to do hard-coded mappings of to reach this IP address, use this DELC, because the only other device in that same subnet on that sub-interface is going to be the one associated with the only DELC that we have on that sub-interface. So we're going to use a frame relay interface DELC statement to tell the sub-interface what DELC it owns, and it knows exactly which DELC to use. So we don't have to, there's no inverse ARP needed or used with a point-to-point sub-interface because there's only two ends. It's not a multi-point interface. So with frame relay, there's lots of acronyms that are flying all around. You know most of the basics already. So let's just do a quick review. A non-broadcast multi-access network, like frame relay, means it's non-broadcast, which implies you may not have virtual circuits between all devices. Maybe a hub and spoke as a good example. And it's multiple access, meaning there's more than two devices on the same logical network infrastructure from an IP perspective. A data link connection identifier is the way the service provider is going to label the ends of the PVCs as they come into the router. So you might have DELC 501, DELC 502, DELC 503 that identify three unique PVCs, but at the far ends of those PVCs you may have some other completely different numbering system. We only need to worry about the local DELC as an ingress point to reach the party on the far side. Also, the LMI, the local management interface, that's really the language of love between the edge of the frame relay switch and our router, which is where frame relay really happens, because in the heart and gut, if you will, of our frame relay network, they could be doing other things. They could be doing ATM and other technologies that are transparent to us. So ATM, our frame relay, really is the protocols that we'd use between us and the edge of the service provider and their frame relay switch. And LMI is the messaging and control channel, if you will, for that conversation. The DCE, which is the service provider, data communications equipment, they provide clocking to us, and our routers at the edge would be DTE, data terminal equipment. And that's the basic foundation for the frame relay setup that we have. So let's talk a little bit about this frame relay LMI. Again, it's the language of love, the control channel between our router and the edge of the frame relay switch. If we turn on encapsulation for frame relay, LMI is automatically enabled, and there's 3 different flavors of it. But the cool thing is, ever since like iOS 11.2 or something way a long time ago, your router will automatically sense which flavor the switch is using, the frame relay switch, and will automatically use that. Now, as far as your status of your PVCs, which is what the LMI part of its job is doing, saying I've got PVCs available, it would show one of three states: active, inactive, deleted. Active simply implies that my router is configured to use a specific DELC, the frame relay switch knows about the DELC, and very possibly, not for sure, but possibly the other side is okay too. See, our frame relay switches may not be all self-contained. We may have a local frame relay switch, and it may go through two other service providers, and the other far side, it may be a totally different service provider. We may not have end-to-end knowledge that the PVC is solid. So that can't always guarantee that our PVC is happy. But active simply does mean that it's providing a PVC to us, and that's good news. Inactive indicates we have a PVC that's being provided to us by the frame relay, but we're not necessarily taking advantage of it or using it. And deleted is where our router believes there should be a PVC. The LMI is saying, no, there's no PVC by that name, and our router output would show as deleted. So those are the three different show frame relay PVC outputs that we can see in the router. We'll take a look at all those two coming up in a quick demo. The address resolution that we talked about earlier hasn't changed, just a little more elaboration on that. If you want to resolve at the headquarters site, for example, which layer 2 DELC I should use to reach a remote site, there's two ways of learning that. And again, this only is applicable if we're on a multi-point interface or a multi-point sub-interface. And the two ways of learning that is inverse ARP, where we actually send out the request, say who's at the other end of this pipe, and the other is a hard-coded static frame relay map. We can verify our mappings, regardless of how they were obtained, by doing a show frame relay map, and that will show us the individual layer 3 addresses and the corresponding layer 2 DELC we would use to reach those layer 3 addresses. So with frame relay inverse ARP, it's enabled by default. Your router will automatically, if it has an IP address on a frame relay encapsulated interface, will send out those requests, again only on multi-point interfaces or sub-interfaces. He's really looking for who is at the other end of this PVC. Well, if we turn off this feature, it simply turns off the local router requesting the actual inverse ARP. It doesn't turn off the response. So on my local router, if I turn off inverse ARP on the interface, I could still have other devices at the far end of the tunnel of the pipe making requests to me, and I would still respond. So the actual syntax really should be no frame relay inverse ARP request, because that's what it's doing. Any mappings that we do learn, let's say we have inverse ARP enabled, any mappings that we do learn are going to be show up with a show frame relay map command as dynamic as their source, and they will also show the keyword broadcast. Now the broadcast, all that means is this, is that if this router has a broadcast / multicast packet, like a routing update that it wants to send, it will take a look at that mapping and say, oh, broadcast for that peer. It will simply wrap up that multicast or that broadcast that would normally be on Ethernet, for example, and it will ship it unicast to the peer at the other end of that PVC. And that's how the broadcast mapping operates for statically learned or dynamically learned maps if they have that keyword broadcast in them. So next what we'll do is we'll do a quick sample with R3 and R5. We'll apply a couple of IP addresses to the interfaces. We'll apply the encapsulation frame relay command to both of them, do a no shut on the respective interfaces, and within about 60 seconds they should have resolved each other's IP address through the process of inverse ARP. Let's take a look at that right now. Alright, so let's go ahead and put some IP addresses on some interfaces and frame relay encapsulation and verify the inverse ARP is working correctly. First thing we should do is before you configure an interface on a new device, this is R3, we should show and see what the status is of that interface. Show run interface for serial 1/0. This is on R3 and it's shut down, no IP address. Great, no problem. So in configuration mode, interface serial 1/0. If it wasn't already shut down, I would shut it down first before you put on frame relay and give it an IP address, because sometimes, not sometimes, quite frequently, if you bring it, have a no shut, and then you do encapsulation frame relay, sometimes the inverse ARP gets kind of whacked out and it'll actually map. Let's say there's 4 PVCs coming into this router. It might actually map all 4 of them with zeros as the reachable address across the pipe. So as a nice safe process, make sure the interface is shut down. You can put on an IP address. This IP address is 155. I'm on rack 8, so I'll put .8.0.3 with a 24-bit mask. And then we'll do the encapsulation of frame relay. That's it, and then a no shut to bring it up. Okay, now that we did a no shut to bring it up, we'll go to R5 and do the same thing, except we'll put on a different IP address. Show run for interface serial 0/0/0. Looks good. We'll do an IP address, and that's going to be 155.8.0.5 because he's R5. And we'll do an encapsulation frame and a no shut. Perfect. So in a moment, we should see that the physical interface came up, and if the frame relay switch is working correctly, we should also see that the protocol, or layer 2, if you will, is going to show up in upstate. And there it is. There's line protocol showing up. Let's do a show frame map, and we don't have any frame relay mappings in place yet. It should take less than 60 seconds for the inverse ARP process to resolve the peer on the other side. We'll stick right here on R5, and there we go. There's our frame relay map. So serial 000, I learned about the peer 155.8.0.3, who's R3, and the DELC I'm going to use to reach that destination is DELC 503. It was learned dynamically, and the broadcast option is always implemented with a dynamically learned ARP. So if we were running a routing protocol, any multicast or broadcast for that routing protocol, assuming it was active on this interface, would be sent to the peer R3. So we should also be able to ping R3. We do a ping of 155.8.0.3. That also implies that R3 resolved us. Let's go take a look at R3. So here's R3. We'll do a show frame map, and there is our dynamic mapping. And it says on serial, on R3's perspective, off serial 1/0, I can reach 155.8.0.5. The local DELC I'm going to use to reach that device is 305. It was dynamically learned, and the broadcast keyword is on as it's dynamic. And if we do a show frame relay PVC, it's going to show us all the PVCs that are available to us. We have one that's active locally. That's the one we're using, DELC 305. That is in place. We have 3 that are inactive, meaning that LMI is telling us about them, but we're not using them. And then we don't have any that are deleted. If we had some that were deleted, that would be us, the router, thinking that we should have them, but the LMI is saying, sorry, it doesn't exist. And here's the details for each of the DELCs, even though we're only using this one right here. So it's active and on serial 1/0, and we have, so here's our traffic stats for it as well. Okay, so that part works great. What else do we have as far as options? We have the option of doing a static mapping as well. If we don't want to use inverse ARP, we could use simply a static mapping. Let's take a look at the syntax next, and then we'll come back and we'll do a live demo. We'll replace the dynamic mappings with static mappings. So static mappings are so easy. It's simply a how do I reach this destination statement. For example, we'd go to the interface that's using frame relay, and we'd say in interface configuration mode, frame relay map, the protocol we're using, which is going to be IP. We're not doing AppleTalk or IPX. Then the IP address we want to be able to reach, the DELC, which is 123, we're going to use to reach that destination, and then the keyword broadcast, which says, hey, any multicast or broadcast type frames that I have, go ahead and ship them down to this peer at 1.2.3.4. Let's replace our static mappings our dynamic mappings that we just created, that we just learned, and hard code them with static mappings. Let's do that right now. All right, so let's remove the dynamic mappings that were learned by inverse ARP and replace them with static mappings. Again, the whole purpose of having these mappings, whether they're learned dynamically or whether they're put in statically like we're going to do, is so that this router knows the correct DELC to use, if there's many to choose from, to reach the peer at the other side. So just as a confirmation, let's do a show frame relay map, and there's our inverse ARP dynamically learned mapping. And let's go into interface configuration mode for serial 1/0, and we'll simply do a no frame inverse ARP. That will turn off R3 from asking. And we'll do the same thing over at R5. We'll go to R5, go to interface serial 0/0/0, and do a no frame relay inverse ARP. So neither one are going to start asking anymore. We'll also do a clear frame in ARP, and what that does, it removes the frame relay mapping, that the dynamically learned mapping that was in place. Do no frame. Let's see, what was that command? Was it clear? There we go. No clear frame in ARP. And I don't need a no in front of clear. So, well, here we go. Clear frame invert. If we do a show, do show frame map, you'll notice that our frame relay mapping is no longer present. It's gone. And it's not coming back because R3 and R5 are not asking for it anymore. So in interface configuration mode, let's do our static mapping. So from R3's perspective, we're going to say frame map IP, because that's the protocol we're using, to reach 155.8.0.5. I want to use DELC, and the DELC we can see right above was DELC 305, and we can add the keyword broadcast on it. So any multicast or broadcast frames appropriate for that interface would simply be unicast down the pipe to the peer at 155.8.0.5. So that's half of the mapping. Let's go to R5 and map a static map back to R3. So frame map IP, the IP address is 155.8.0.3. We're going to use DELC. If we look, if we recall what the DELC was, it was DELC 503. That's how we have the frame relay switch set up, and we'll use the keyword of broadcast. Now we have frame mappings in place that are static. If you'll notice, this is the really only thing that changed. It's static, and we have the keyword broadcast because we hard coded it. And to reach 8.03, we'd use DELC 503, and we can verify that with a ping. And the crowd goes mild. So that's how we do static mappings. Now, one other thing that can happen in your environment is that if you bring up an interface and it's not shut down and you put encapsulation frame on it, you might get mappings to 0000 for all of your DELCs. Say you have 4 DELCs that are coming in from the switch, and to get rid of those, simply finish your configuration. If you want to use inverse ARP, that's great. Save it, and really the only way to get rid of those 000 mappings is to save your config and reload your router. There are a couple other ways you can get rid of those, but what I do to keep it safe is I make sure an interface is shut down before I put frame relay encapsulation, put the IP address on it, then I do a no shut, and then the problem can go away. You can also include the no frame inverse ARP in interface config before you do no shut, and that will make sure that you don't request any layer 3 to layer 2 mappings from a frame relay perspective. And we also discovered here in the demo how we can clear with the clear frame relay in ARP command to delete dynamic mappings. So what about point-to-point interfaces? Let's talk about that next. If we have point-to-point subinterfaces, we don't need any dynamic mappings whatsoever. In fact, we don't need any mappings at all, because if we have a point-to-point network, that implies there's only 2 devices on that one logical layer 3 network, and that's the 2 devices at the end, or the ends, if you will, of our PVC. So in a point-to-point environment, the way we create point-to-point interfaces is we have to create a sub-interface. Enable frame relay on the parent interface. Make sure the parent interface is in a no-shut state, and then we simply say interface, for example, serial 0/0/0/0 dot and some number, and then we'd specify point to point. When we create, the very first time we create a sub interface, we get a choice. Do you specify it as point to point, meaning it's just me and whoever's at the other end of the tunnel, or do we specify multi-point, which means we could terminate multiple virtual circuits on this one logical interface? So with point to point, it's only me and the person on the far side, that's it. So we don't need to do any frame relay map statements. Inverse ARP won't apply, but we are going to use the frame relay interface DELSI statement. It just tells that subinterface, guess what? This is your DELSI. So if it ever needs to reach a device on that same logical subnetwork, it knows the layer 2 address to use, and that's the DELSI we assign it. Let's carve out next point-to-point subinterfaces between two routers. We'll go step by step and take a look at how easy it is to pull this off. So all we're going to do with point-to-point subinterfaces is simple. We're going to remove the IP address off the physical interface on R5 and off the physical interface of R3. We're going to leave the encapsulation of frame relay on that physical interface, and we're also going to leave it in a no shutdown state so it's up and available. And then we'll create serial interface 0/0/0.1. We could choose any number we want and specify that it's going to be a point-to-point subinterface. We're going to assign the IP address to the subinterface, and we're going to use the frame relay interface DELSI statement so that R5 knows that this subinterface owns DELSI 503. It also will know that if it needs to reach 155.8.0.3, it would say, oh, that's off this logical interface, this is the DELSI I'm supposed to use, and it would shoot it down that DELSI. That's why subinterfaces, if they're point-to-point, we don't need to have any frame relay or mappings because there's only one layer 2 address associated with anything on that subnet, and that would be the DELSI we assign with the interface DELSI statement. Same thing with R3. We'd take off the IP address off the physical interface, make sure frame relay is there, make sure that we carve out the sub interface with point to point, use the frame relay interface DELSI statement, and then this sub interface knows that its only shot at life is DELSI 305. And those two devices would be able to talk happily across that. So without further ado, let's go ahead and create that. So to take full advantage, what we're going to do is we're going to default the interfaces, and then you can see the step-by-step process. We're sitting at R5. We'll go into configuration mode and do a default interface for serial 0/0/0. That will guarantee that everything has gone off that interface. If we do show run interface serial 0/0/0, we'll see there's no longer anything there. It is, however, in an up state. So we'll go into interface serial 0/0/0. I'm going to do a shut, just like I said, best practices. If I don't want inverse ARP at all on the interface, I would do a no frame, encapsulation frame, and then a no frame relay inverse ARP. So it won't ever even make a request. We're not going to need them, and this way it won't accidentally get a whole bunch of erroneous mappings on the physical interface. So now that we have the no frame relay inverse ARP set up and its encapsulation with frame, we can do a no shut, and then we can create the sub interface. I'm going to exit out to global config, that way we can see the options. If we do interface serial 0/0/0.1 space and a question mark, it'll give me point to point or multi-point. Simple. If you are talking to the other party and the other party is simply the only other device on this logical subnetwork where this interface is, point to point is your man. And if you're at a headquarters site and you have multiple locations that you're going to be talking to with multiple PVCs, you'd want to set up as multi-point. So we'll set up as point to point, press enter, give it an IP address. This is R5 and he's going to be 155.8.0.5. And then this last command, IPO, it says it wants a full add there. And we'll put the 0 at the end. Okay. And then the last thing is we need to tell this subinterface that it owns DELSI 503. Because by default, all DELSIs are assumed to be at the physical layer, meaning at the physical interface. So unless we pull that delc down and assign it to this subinterface, it won't know, this subinterface won't know to use that delc. So the syntax is frame relay interface delc, and then you specify the delc you want to use. And that's it. So this subinterface has an IP address. It knows what delc to use. And now if we do a show frame relay map, it's going to say, oh, look, I've got this delc 503. It's assigned to the subinterface 000.1, which is a point-to-point subinterface. And broadcast, if you'll notice, we didn't have to add that. That's a default for a point-to-point subinterface. So all we need to do is on R3 is the same process. On R3, we'll default the interface serial 1/0. We'll go to interface serial 1/0. Make sure it's shut down. We'll do an encapsulation of frame relay on the parent interface. No frame relay inverse ARP, and a no shut to bring it up. Then we'll create the new subinterface. Interface serial 1/0, and we'll use .1 just for grins and specify the type. Now the second time you go into the subinterface, we don't have to specify it's multi-point or point-to-point. It knows. But on creation, like right now, of that subinterface, we need to tell it what type it is. So great, it's a point-to-point subinterface. What information do we need to apply? An IP address would be great. And the frame relay interface delc statement telling this subinterface who owns or what interface what delc it's going to use for this subinterface, which is 305. And now if we do a show frame map again, it has this subinterface point to point. It owns delc 305. It's going to be broadcast based, meaning if it needs to send multicast or broadcast type traffic, it's going to unicast it down this pipe. So it really doesn't care who on the other side gets it, but it's going to send it. And that's how it operates. So let's test this with a ping. We should be able to ping to 155.8.0.5, which is R5 on the other side of the frame relay. And that is the point-to-point subinterface. So no frame relay mappings, no inverse ARP, but the mappings logically become available because we are associating a delc with a specific subinterface. So what about corporate headquarters where we have perhaps a multi-point subinterface? The good news is that a multi-point subinterface works exactly the same as a physical multi-point interface. When we create the subinterface, instead of saying point-to-point, you'd simply say, for example, on R3, interface serial 0/0.2, and then say multi-point. And then you do your frame relay mappings, or you could use inverse ARP. Either way, it's exact. So when you do a multi-point subinterface, think of it as if you're on the physical interface, because the process of needing manual mappings or inverse ARP still holds true. So let's convert this now to a multi-point subinterface. It'll be fairly easy to do. On R3, we'll just go into configuration mode and say no interface serial 0/0.1. No interface serial. What interface was it? It was on R3. So it was interface serial. It's always good to get the right one. 1/0.1. Okay, and it's saying, warning, not everything may be removed until you reboot. That's okay. I can live with that. We'll use a different number. So now I've got no subinterface. If I do it, do show IP interface brief, I've got this deleted entity, but I've got nothing with the 155.8 subnet on it. So if I wanted to create a multi-point subinterface, I'm going to go into, let's also do a do show run interface serial 1/0. And if I wanted to use inverse ARP on my subinterface, I would need to turn it on here. So let's turn on inverse ARP. So interface serial 1/0. We'll do a frame relay inverse ARP, that enables the feature. So there's no major IP address, no IP address on the major interface. Inverse ARP is enabled and frame relay is enabled on the major interface. So we'll go into interface serial 0 slash, I like 0, 1/0.2, and we'll create a new multi-point subinterface. And we're going to do an IP address. IP address of, we're on R3, which would be 155.8.0.3. And let's do a frame relay map here, because that would be best practice. Let's do a hard-coded frame relay map to this subinterface so that it knows exactly what DELC to use to reach its peer. If this looks identical to what we've done in the physical interface at this point, it is. Frame map IP of 155.8.0.5 is going to be using DELC 305, and if you want broadcasts, you put the broadcast keyword on it. That's it. So we do a show run interface serial 1/0. It's up. It's got encapsulation frame relay. If we do a show interface for serial 1.0.2, which is our multi-point subinterface, it's got the IP address and it's got a frame relay mapping saying that this interface is going to use DELC 305 to reach 155.8.0.5, with our address being .3. So on the other side, if we wanted to, we could change that point-to-point subinterface. But check this out. Even though R3 has a multi-point subinterface and R5 has a point-to-point subinterface, they both have mappings. So if we look at this mapping, R3 knows how to get to this IP address through DELC 305. And if we jump over to R5 and do a show frame map here, this guy has a point-to-point subinterface and it's using DELC 503. And if we do a show IP interface brief, and we'll exclude the unassigned addresses, he says, well, to reach 155.8.0.3, I'd use this interface. It's on the same subnet. And then he would look at that interface and say, well, that interface is supposed to use DELC 503, and it would have complete resolution of being able to send a packet out that correct DELC. So even though we have two different types on two different sides, there's a possibility this could still work. So let's go ahead and ping 155.8.0.3, and the traffic flows no problem. See, the whole thing with layer 3 to layer 2 mappings is it's locally important. So as long as R5 knows how to reach and which DELC to use to reach a certain given network, it's great. As long as R3 knows which DELC to use to reach a certain given destination, that's great. The challenge is going to come in a different area, and that is your routing. Because with routing updates and who's the next hop and so forth, there adds a tweak to it. So we'll save that discussion of routing for a different segment. So we've taken a look at how to do subinterfaces multi-point with mappings. We've taken a look at how to do subinterface point-to-point using the frame relay interface statement. We also took a look at setting up frame relay on the physical interfaces, which is just like multi-point subinterfaces, which can use inverse ARP to resolve the layer 3 to layer 2, or they can use the static mappings as we did with the subinterfaces with the multi-point. So again, the whole deal is that it's locally significant as we resolve. I mean, we could have a physical interface connected to on the far side, a multi-point subinterface, or a point-to-point subinterface to a point-to-point subinterface to a multi-point subinterface, as we just demonstrated. It's not really that critical as far as basic connectivity, but it does have some implications on routing later. So in a full environment, let me show you one more trick that's really important, and that's this. Frame relay is interesting. If I do a show frame relay, if I do a show frame map, and I do a show frame PVC, which are both great commands, it's going to show me my status. So it's basically saying here that I've got one active PVC, and here on R5, if I do a show frame PVC and I include DELC 503, it'll give me status on that specific DELC, and that's wonderful. DELC 503, its usage is local, it's active, here's the interface that owns it. Life is absolutely terrific. There's some packets that have gone across based on our pings that we've done back and forth. That's wonderful. Now, the challenge here is that we may be going across multiple providers. I mean, maybe our frame relay service provider is AT&T, but on the far side, the frame relay who's actually delivering it to the far side customer, which is also possibly us, is Sprint, or maybe Sprint's in the middle. Now the LMI, as they communicate information on this PVC, maybe our local frame relay provider doesn't have the full story. Maybe there's more going on as far as the far side. So even though it says active and that this PVC is happy and things are okay, we could have a situation where it says active and there's still LMI coming into our local router, but in reality the far side isn't happy and there's a problem with connectivity. See, our routing protocols are not going to know that. They're going to say, well, layer 2's up, layer 1's up, I'm going to use this interface. So we have to have some mechanism, some out of band, if you will, mechanism for testing whether or not full reachability is available. And we can do that with something called end-to-end keep alives. And here's how it works. We're going to demonstrate here in a moment. End-to-end keep alives have three different roles we can play. R5 could be a requester. If R5 is a requester, that would make R3 the replier. So R5 was in requests and R3 was in replies, and they both would keep track. And if so many responses and so many replies came in a certain window, they would say, okay, this link is still up, things are good. If we missed the window, for example, we send some requests and the replies don't come back after the window closes of so many errors of not getting responses, we would signal the layer 2 protocol as down. And that way your routing protocols can figure out, oh, you know what, we're down. And they can make other routing path decisions. Otherwise, your routers may never know that there's a problem and they may still consider a bogus or invalid interface as a valid traffic path. So that's the benefit of using end-to-end keep alives. I mentioned there was a request and a reply. There's also two other options that are important to be aware of. One is bidirectional. We could specify that both endpoints are sending requests and both endpoints should be prepared to send replies. That's the bidirectional mode. And there's one last mode. It's request on one end and a passive reply on the other. So if R5 was a request and we set up R3 as a passive reply, R3 would reply, but it wouldn't keep track. Oh, I should be getting a new request now. Oh, I should be getting another request. It doesn't keep track of counters or errors or anything else. And that would leave R5 to do all the heavy lifting to determine if the path was still up. So how do we implement end-to-end keep alives? It's really, really simple. Let's do it right here on R5, and we'll set R5 up as bidirectional, and we'll set up R3 as bidirectional. So they'll both be sending keep alives, looking for responses, responding to each other, and keeping a window of whether or not we have successful keep alives going on. In configuration mode, we're going to make a map class, which is different than a class map, which identifies traffic. But this map class, we're going to do it for frame relay, and we're going to call it my map class. And that puts us into map class configuration mode. Then I'm going to specify frame relay, end-to-end, keep alive mode, and take a look at this. Here's our options. Bidirectional, meaning both are sending requests and both are prepared to send responses to the other's request. We could do passive reply, which would be for one side to be the reply side, not keeping track, and the head-end site, for example, to do request onlys. And we have the normal request and reply. So the valid combinations would be this. We could have bidirectional on both sides. We could have request on one side, reply on the other side, or request on one side and passive reply on the other. That's how those would pan out. So let's specify bidirectional. And now that we have this map class created, we'd go ahead and apply it to the interface that's using frame relay. So if we went to interface serial, this is R5. So if we go to interface serial 0/0/0.1, I've got too many zeros in there. Like that. To apply it, we'd say frame relay class, and we'd say my map class. Of course, using whatever name you created. Just like that. If we do a do show history, I can save a couple commands by creating the same map class over on R3. So I'll just copy that. We'll go over to R3, and R3 will go into configuration mode, paste that same map class in, and then go to interface serial 1/0.2, which is our multi-point sub interface, and we'll simply apply the class map. Frame relay class, and it's my map class. Just like that. So now we have these keep alives that are going back and forth. If we do a show frame PVC, let's take a look at this. So we have our PVC information just to verify that we're active, the interface is up and happy. Again, DTE would be our gear. The DCE would be the frame relay switching that's actually providing the actual clocking for us. And if we want to see the actual keep alives, we just show frame end-to-end keep alive, and on this case we say serial 1/0.2. And perhaps I need the keyword interface, then serial 1/0.2. And that would show us the details for the keep lives that are actually going. So right here we have Del C 305, Del C usage local, virtual circuit status, and then we have EEK up, which implements that we haven't had enough errors in the window. We haven't had any errors because they're going back and forth to indicate that the Del C was no longer active, that the line protocol would go down. So that's how end-to-end keep alives work. So in this lesson, we've taken a look at the configurations for all the options for frame relay. Frame relay on the physical interface, frame relay on sub interface. For sub interfaces, point-to-point or multi-point. We've identified that we need mappings for any multi-point type interface, either the physical or multi-point sub interfaces. Mappings come in various flavors. We can use inverse ARP, or we can use hard-coded static mappings. The broadcast keywords allows things like routing updates and so forth to work across it. We do not need to do hard-coded mappings or rely on inverse ARP for point-to-point sub-interfaces because we use the frame relay interface Del C statement, which tells that sub-interface, which is point-to-point, the only Del C possible to use because it can't terminate multiple PVCs on a point-to-point sub-interface. And that's it. I appreciate you joining me for this discussion on frame relay.